Okay, continuing where we left off in class before, we had introduced the idea of finding a tangent line slope on a curve. Very quickly, that's what I'm highlighting right here. It was a limit definition. It's the slope of the secant line as that point Q is approaching P, and we need a limit to be able to do that. But we looked at example 1 and we came up with this radical function, f of x equaled radical x. Given the point a comma root a on it, the point of tangency we proved was 1 over 2 radical a for its slope, for the slope of that tangent line at that point. So we'd like to be able to write the equation of a tangent line at that given point. And something to really help you out with, anytime we write the equation of a line in calculus, we use point-slope form almost always. And we're given an initial point, x1, y1, that's 9, 3. We could immediately even substitute that in to our point-slope form right now. But I guess what I'd really like to show you is that you just saw a moment ago that the tangent line slope m was equal to 1 over 2 root a, and this is where a would equal 9. Now if that's the case, we can see the tangent line slope is 1 over 2 times the square root of 9. Square root of 9 is 3, 3 times 2 is 6, we'd get 1 over 6. So I know that's my m. That's my tangent line slope. I have a point 9, 3. My x1 is 9. My y1 is 3. Here it is, very, very, very quickly, my equation of a tangent line. Okay, now in Calculus AB, we are going to focus on motion that travels in a straight line. Almost always that will be either in a horizontal line or a vertical line. That being said, we're going to investigate average velocity. And if you were studying physics, this wouldn't be anything new to you whatsoever. Average velocity on a given time interval would just be the change in the distance divided by the change in the time. For example, in this little picture here, or this little example, find the average velocity of a car that travels 200 miles from a time period of 9 a.m. to 1 p.m. Well, look, from 9 a.m. to 1 p.m., look at this. From 9 to 12 would be 3 hours. 1 more hour would be 4 hours. What's the change in the time? Very simply, 4 hours. How much distance was covered? What was the change in the distance? 200 miles. 200 divided by 4 would be 50, meaning this would be a 50 mile per hour average velocity. Please understand, this in no way implies that the car was always traveling 50 miles per hour. The car could have been traveling 65 miles per hour at 11 o'clock, for all we know. Maybe the car was traveling much more slowly at an earlier time. That would be an instantaneous velocity for a given instant. And we're going to investigate that very soon. But remember, this is just an average velocity on a given time interval. Look at the next example. If a car traveled 80 miles total from 9 a.m. to 10:30 a.m., and then we learn at 10:35 it had traveled 85 miles total, find the average velocity from 10:30 a.m. to 10:35. Well, we could say, what was the change in the distance? Well, going from 80 to 85 would be an increase of 5 miles. From 10:30 to 10:35 would be 5 minutes. Now this would be an average velocity of 1 mile per minute on the time interval from 10:30 a.m. to 10:35. But what we could do is maybe make a little bit of a unit conversion. There are 60 minutes in 1 hour, and you could very quickly then confirm that from 10:30 a.m. to 10:35, granted that's just a very small time window, but in that 5-minute interval, the average velocity was 60 miles per hour. Like I said before, that wouldn't mean that the car was always traveling 60 miles per hour from 10:30 to 10:35. This is leading us again to talk about instantaneous velocity. On the second page, let's assume that we have a position function where you plug in a given time and you'd be given a certain position corresponding to that time. By the way, graphically, what that would look like is time would be graphed on the x-axis. Right here we'd have position. Now position might be even in miles. Perhaps over here time is in hours. Could also be in feet and seconds or meters and seconds, whatever you'd like. But that being said, if we'd like to find the velocity at a particular instant, what we're going to do is go back to this limit definition. What we need to know is that the instantaneous velocity is the slope of a tangent line. Every instantaneous rate of change is going to represent the slope of a tangent line. Think about it. If I had some kind of a position curve, and if I wanted to find a tangent line slope is change in y over change in x. That would be miles per hour. If I were dealing on a particular time interval from time A and time B, that would be a secant line slope. That's your average rate of change. So an average rate of change is simply y2 minus y1 all over x2 minus x1, a secant line slope. An instantaneous rate of change is this limit. So let's very quickly take a look at example 2. Mel drops a football from a blimp 600 feet above the ground. The function s of t represents distance from the ground in feet after t seconds. And it's given to us right here. S of t equals negative 16 t squared plus 600. Find the velocity when t equals a. A very arbitrary a seconds. We don't necessarily know what a is. It could be any given defined time. But notice it's not a time interval. It's an instant. What does that mean? It means we need this limit definition. And we're going to find, in essence, the slope of a tangent line. So now look, what you really are going to have to do is plug in a plus h into your position function right here. Plug in a plus h for t. What do we get? Negative 16 times a plus h quantity squared plus 600. Now say minus. Now plug in s of a. I'm going to throw in some brackets. Maybe you'll see why in a minute. Plugging in a is easier, of course. But I'm going to have to subtract all of that. And that's why I'm putting some brackets around it. Now, the a plus h squared, I'm going to write up here in this top right corner just to help us out. Hopefully you know we've dealt with so much algebra in this class already. Very basic definition, a squared plus 2ah plus h squared. If I were to multiply negative 16 out in front, what would that look like? Well, just distribute that negative 16 everywhere. Negative 16 times 2 is negative 32. And then we'd have negative 16h squared right over here. And then we'll have our plus 600. We can't forget about that. Now distribute that negative, and you'll get a plus 16a squared minus 600. Distributing that negative, that's why I put those brackets around there. I hope it's really clear why I did that. Look, negative 16a squared and a plus 16a squared goes away. 600 and a negative 600, they cancel out. And you'll notice quickly that the numerator, if I let h go to 0, would be approaching 0, as well as the denominator as well. 0 over 0 is undetermined. How about we divide everything by h, and we'd be left with negative 32a minus 16h. As h would approach 0, we would have negative 32a. So at t equals a seconds, that's where we're going. Now for part B, very quickly, that's what a is. A is 3. So negative 32 times 3, well, that's negative 96. Let's pay attention to units. Feet per second. Just like I drew, look right above us in that picture of position. Right now it's feet per second. The slope of the tangent line is change in y over change in x. And at that particular instant, we'd have a negative 96 feet per second. The negative is indicating a downward direction, by the way. All right. Well, from here, when does it hit the ground? When it hits the ground, what is its velocity? When it hits the ground, I hope you would agree, your position, your distance from the ground, s, would be 0. So you got to do a little bit of thinking here. Set s equals 0, and you have this equation. We're going to solve for t. Normally, if it's a complicated quadratic, you can feel free to use your quadratic program on your calculator. Here, I think it's just as easy to just solve by hand. Take 600 divided by 16, and we could do that super fast. Let's do that. Looks like 37.5. And then we're going to have to take a square root. You know the square root of 36 is 6. You might expect it to be pretty close to that. So let's bring that back. Second answer, square root of that, 6.1237, something like that. That many seconds. That's when the football hits the ground. But again, what's the instantaneous velocity? Negative 32 times a at a seconds. A is equal to this 6.1237. Tell you what we're going to do. We're going to take that time, that a value, multiply it to negative 32 and negative 195.959. Negative 195.959, and that's feet per second. So that's when the object hits the ground. Okay, so what's the big picture here? Calculus deals with change. Velocity is just one example of a rate of change. We're going to study so many of them. Let f of x be defined on an open interval. The average rate of change is the secant line slope. It's the secant line slope. Plain and simply, if you're given 2 points, you can just go back to algebra 1 and do y2 minus y1 all over x2 minus x1. If you are interested in a particular instant, not over a time interval, but at a particular instant, you're going to have to go back to this limit definition. You're going to be going in the direction of finding the tangent line slope. Very, very big difference. And really, we're going to be taking a look at just one last example and working this all through. We're going to find the average rate of change and also an instantaneous rate of change. We're actually going to do that on our second video. We might as well just stop right here and start anew. So we'll see part 2 in just a moment.